This video lecture I will talk about random variable having normal distribution. So I will continue this topic. Again, we have random variable x, which has normal distribution with mean value mu and variance sigma squared. So what does it mean? It means that probability density function of x has the following, is given by the following function: 1 over sigma times square root of 2 pi e to the power of minus half x minus mu over sigma squared. What the meaning of mu? Mu is expected value of x, and mathematically it's represented by the following formula: integral of x times f of x dx from minus infinity to plus infinity equals to mu, its expected value. And what we can say about sigma? So what about sigma we made? So sigma tells us how close observed values of x appear to be to expected value mu. And in the last lecture, for example, we seen the following fact. So if x small is observed value of random variable x, then probability that observed value of x is between mu and minus 1.96 sigma and mu plus 1.96 times sigma is equal to 0.95. So in 95% of cases, observed value of x will be in this range, in this interval. So sigma says how close our observation to appear to be to expected value mu. Assume we have a random variable which has a normal distribution, or believe it has a normal distribution, but we don't know what is its expected value, what is mu. How we can measure this mu? So to measure mu, what we do is we make, say, n observations of random variable x. If, for example, random variable x defines height of students, and we just take n students and measure their heights, and what we get is n values: x1, x2, x3, so on, xn. We can find mean for these n values, 1 over n times sum of all these values, and what we know about mu by definition of mu, by definition of mean value for random variable, mu equals to limit of this mean value for sample of size n when size of sample tends to infinity. So this is what it was basically definition, and from this definition of mu we get this formula. But in reality we can't measure, we can't make infinite number of measurements. We always have finite n. In reality, in practice, n is always finite. It's always finite, and if we make another n observations, this x bar will have different values. So what we want to know, what we want to investigate, we want to analyze properties of x bar. And this is what is called sample mean, and we want to find out what is this distribution of this sample mean. So now we introduce another random variable, x capital bar, which is represented by a combination of n random variables we introduced before. Namely, we take mean value for these random variables from 1 to n here. Now, once again, when we make first measurement is in terms of these random variables is finding value of x capital 1. Making second measurement or second observation is finding value of x2. Therefore, when we make n observations, we get one value for each of these random variables. And all random variables have the same distribution as our original original random variable. And this is just another way of representing the procedure when we just make n observations of our original random variable. Now, anyway, we got new random variable x capital bar, and this x capital bar is what we're interested in. We want to know properties of x bar. Couple of things we can find out straight away. For example, we can find out what is expected value of x bar, expected. So this expected value is expected value of x bar, which is given as combination of xi's. Now we remember property of expected value. Expectation of linear combinations is linear combination of expectations. It is 1 over n times sum of expectations of xi's for all random variables xi's. Now, since all xi's have normal distribution with expected value mu, then all of them all of this equals to mu, and thus we will have 1 over n times n mu equals to mu. So what we have proven? We have proven that expected value of x bar equals to mu. So this property was proven in lecture notes 4. So proof of this is in lecture notes 4, pages 5 and 6. You can check it. Now we can find out what is variance of x bar. Variance of x bar is variance of, so here we put definition of x bar is 1 over n times sum of xi's for I from 1 to n. And here, to find out this variance, we will use properties of variance, which we also found before and highlighted in lecture notes 4, page 8. So this constant here should appear before variance squared, 1n squared. And here we will have, since all xi's are independent random variables, I forgot to mention it, but it's obvious from the procedure we follow, this will be equal to sum of variances of xi's for all n random variables. So this will be equal now 1 over n squared times n sigma squared, or this equals to sigma squared divided by n. So what we got? We got variance of sample mean equals to sigma squared over n. Sigma squared is variance of x, and n is size of our sample. Next statement is very important, and although it comes without proof, you should remember this. So x bar has normal distribution. And since we found already expected value for x bar and its variance, we can put it like this: it mu sigma squared over n. So this is distribution of sample mean, this formula for distribution of sample mean. So this means that probability density function for x bar has this kind of representation. It's square root of n divided by sigma times square root of 2 pi e to the power of minus half x minus mu squared divided by sigma squared divided by n. So proof of this statement, that x has normal distribution, is quite difficult, and there are simpler ways, there are certain, reasonably simple ways to prove this, but this involves certain technique which you don't know for now, but which we will learn later. And this technique is called moment generation, so it involves moment generation functions. Let us find sample mean distribution for this example. Weights of packets of breakfast cereals are normally distributed with mean value 508 grams and standard deviation 5 grams. A sample of 100 packets is taken at random and weighed. So what we want to find? We want to find distribution for sample mean x, which is mean for 100 pockets. So what we know that x bar has normal distribution with expected value mu, which is the same as for each of these packets of breakfast cereals, and variance sigma squared over n. Now mu is given here is 508 grams, and sigma is given is 5 grams, and therefore we can say n is 100. Therefore x has normal distribution with mean of value 508 and variance 5 squared divided by 100, which is finally normal distribution with mean value 508 and variance 0.25. So as you can see, this variance is very small, and when we take 100 packets and find mean value for these 500 packets, then we get a mean value which should be very close, which has very localized distribution. So this will be like this. So probability density function will be like this. 508. So this this spread is very small. We can also make certain conclusions not only about sample mean, but about sum of values in a sample. So sum, let's consider sample of size n, again we consider, which is given by values for n random variables which have same, so x1, x1, x2, xn. So these have the same normal distribution and independent. Now I didn't forget to tell this, to point out to their independence. Xi has normal distribution with expected value mu and variance sigma squared. Now what we know that x bar has normal distribution with expected value mu and variance sigma squared divided by n. Now let's introduce random variable s, which equals to sum of xi's. So as we can see, it is n times x bar. And now it should not be difficult to prove, but anyway we will skip it. If x bar has normal distribution, then s should also have normal distribution, because it's one is just multiple of another. And let's find expectation and variance for s. Expected value of s equals to expected value of n times x bar, which is n times expected value of x bar, and expected value of x bar, we know it is mu, therefore this is n mu. And variance of s is equal to variance of nx bar. This is n squared times variance of x bar, and variance of x bar, we know it is this sigma squared divided by n, therefore it will be n squared times sigma squared divided by n, or this equals to n times sigma squared. And from here we conclude that s has normal distribution with expected value mu and n mu, and variance and sigma squared. And you will need to use this formula when you solve problem 2b in problem sheet for tutorial number 5. Now we are getting to very important generalization of what we found about sampling distribution of sample mean, which is called central limit theorem. Again, consider random variable x . Consider samples of size n and sample mean. So sample mean x is a random variable which is introduced the way we did it before. So what we know, if if X has normal distribution, then X bar also has normal distribution with the same mean and slightly different variance. What is central limit theorem talks about that even if X is not normally distributed, X bar has approximately normal distribution. If n is large. Formally, central limit theorem can be stated like this. Consider n independent random variables x1, x2, so on, xn with identical distributions. With identical distributions such that expectation of xi equals to mu and variance of xi equals to sigma squared for all i's. Then x bar defined like 1 over n times sum of xi's will have following properties. Expectation of x bar equals to mu. This is first property. Second property, variance of x bar will be equal to sigma squared divided by n. And third property, as n tends to infinity, the distribution of x bar converges to normal distribution with mean mu and variance sigma squared over n. Statements 1 and 2 proved the same. They have same proofs as I used for proving these properties for normal distribution. Statement number 3 I didn't prove even for normal distribution, and here it is extremely difficult. This part is difficult to prove. We will skip it and we'll take it as granted. Let us apply what we learned about central limit theorem to this example. The number of phone calls received by a counseling service each evening follows a Poisson distribution with mean 4.5. Number of calls are recorded each evening over a 30-day period, and find the approximate probability that the average number of calls per evening over this period exceeds 5. Then what we have? We have x, which has Poisson distribution with mean value 4.5. So we know that variance of x, since for Poisson distribution variance equals to its mean value, so it's also 4.5. It's a property of Poisson distribution. And what we know more, we know that we have a sample of size 30. Then the average number of calls per evening over this 30-day period is sample mean. And according to central limit theorem, expected value of sample mean coincides with expected value of x, which is 4.5, and variance of sample mean is variance of x divided by size of sample. So this is 4.5 divided by 30, which is 0.15. Now, according to central limit theorem, x bar has approximately normal distribution with mean value 4.5 and variance 0.15. And therefore, we can introduce a random variable z, which is given by x bar minus mu divided by sigma divided by square root of n, which has standard normal distribution or approximately standard normal distribution. Therefore, probability that x bar is more than 5, it's what we're supposed to find. Probability, or approximate probability that x bar is more than 5. This equals to probability that z is more than 5 minus mean value 4.5 and divided by standard deviation of x or square root of variance, which is square root of 0.15. This equals to probability that z is more than 1.29. You can check it. And this equals to probability that z is more than this number equals to 1 minus probability that z is less than this number. And this probability that is less than 1.29 can be found from a table for normal distribution, and this equals to 0.9015, and the answer is 0.0985. Let us consider one more example. Service times for customers coming through a store or checkout are independent random variables with mu equals to 1.5 minutes and sigma equals to 1.0 minutes. Find approximately the probability that 100 customers can be served within 2 hours. So in this example, we have some kind of extension of central limit theorem. Here, xi is the service time for customer I. So we have 400 customers, we have 100 xi. So we have I changing from 1 to 100. So for each of these xi's, we already have expectations and variance. Total time required to serve 100 customers is, let's denote it by S, equals to sum of xi's for 100 customers. And this can be represented as 100 times sample mean. So during this lecture we discussed this sum of all values in a sample. So what we learned is that expectation of S equals to n times expectation of xi, which is n times 1.5 here, or n is 100, it's 150, and variance of S is n times variance of xi, so variance for all xi's the same and equals to 1, so this is 100 times 1, so this is 100. Thus, we can state that S has approximately normal distribution with mean value 150 and variance 100. Now we're supposed to find probability that 100 customers can be served within 2 hours, and 2 hours is 120 minutes. Therefore, we're supposed to find probability that S is less than 120. This equals to probability that S minus mu, which is 150, divided by standard deviation, which is 10, should be less than 120 minus 150 divided by 10, and this equals to probability that Z, which has standard normal distribution or approximately standard normal distribution, less than minus 3, this is minus 3, and this, as we remember, equals to 1 minus probability that Z is less than 3, and this is 1 minus phi capital of 3, which is found from table for normal distribution, and this equals to 1 minus phi of 3 is 0.9987, and finally we found this probability that S is less than 120, 0.0013, so it is roughly 0.1%. There is 0.1% chance, roughly 0.1% chance that 100 customers will be served within 2 hours.